Let's see here. I think we should be good to go. All right. Okay, so welcome back once again to another live stream. This actually will mark the third from the last type of AP Calculus live stream that we'll be having here together, because we only have the next Tuesday and Thursday left before the actual test begins for our AP Calculus students. So, as what we've been discussing before, and I've been doing for so many times beforehand, we'll be going over another AP Calculus free response section together, where we can go over each of the problems 2 at a time. This time we'll be going over the 2016 AP Calculus free response questions, so the ones that are listed right here. Again, every packet will have 6 free response questions that we go through 2 at a time, the first 2 of which will have the calculator section. So again, we'll be going through the steps with our trusty TI-83 Plus, and we'll be going to see how we can answer each question as thoroughly as possible and correcting as we go along as we go through this exam together. So, as we have done before, I will list out all of 6 of the questions here so that we can go and see the actual amount of points that we have achieved. I think this is all out of 54. So we'll go and see what we have fully achieved once we go through this entire exam together. Alright, as always, you can submit any of your questions through the email labcoatmath@gmail.com down on the bottom left side as we go through each problem, or again, anything through the chat is always welcome as well, as we can go and try to see how we can answer any questions that are sent our way through there as well. Okay, I think we should be good enough to go. So, as what we've done so many times beforehand, we will be copying over the problems onto our notebook so that we can go through each detail carefully and correctly as we move through this exam. Okay, so let's get started, and we shall begin with our first question here for the 2016 AP Calculus free response questions. So this is 2016 AP Calculus, the free response questions. So let's start with number 1 here. We have a table here. This is going to be T in hours, and then the R of T in the liters per hour. Okay. And our table is filled out from 0 to 1 to 3 to 6 and then to 8. So this is 1340, 1190, 950, 740, and 700. Okay, very good. So with this, we should be good to go to start copying over the problem itself. It tells us that water is being pumped into a tank. This tank is modeled at a rate they call W of T is equal to 2000 times E raised to the negative T squared over 20. Okay, and this is going to be in liters per hour for the interval from 0 to 8. Okay. And then they tell us where T is in hours. Okay. And then they continue that water is being removed. At a rate. This is going to be R of T, which again they show in terms of the table in the table. Okay. Next, they're going to lastly tell us that at the time is equal to 0, there are 50,000 liters of water in the tank. Okay, very good. So that is what we have listed out here so far. So let's go over to part A for this, that we need to estimate r prime of 2. Okay, and then we want to indicate units of measure. All right, so if we are looking to estimate r prime of 2, of course that means that we are going to do an estimation of the average rate of change. So this is average rate of change being asked for. In this case, for the difference between points 1 and 3 will be the best, right? Because it's 2 right in the middle. So if we're going in between 1 and 3, this is going to be average rate of change equation of r of 3 minus r of 1 all over the difference of 3 minus 1. Okay. Now let's keep track of the units here for the sake of the question as well, asking for the units of measure here. So R again was already listed as the liters per hour on the numerator, and we're dividing by the difference in time because this is the average rate of change for the x value of that table that we have. So this is going to be in hours again, meaning that once we plug in here, this is going to be left in liters per hour squared. Again, hours twice in the denominator, making it squared. So R of 3 minus R of 1 is going to be the injected from the table of 950 minus 1190, all in the numerator, divided by the difference of 3 and 1 being positive 2. Then, by going through that, this is going to be the remainder here. We can go through our calculator as well to double check on this, but in any case, so this is going to be a negative 240 all over 2 liters per hour squared, which is going to be negative 120 liters per hour squared. Okay. Thankfully, this is a calculator section, so we can double check our work with what we have on the calculator here. So clearing that out, this is going to be all of 950 minus 1190, all divided by 2. And that is not correct because I did not show that properly with the work. The parentheses must be closed off here. So, what is happening here? 190, please. There we go. Okay. So with that, the last one, right? 950 minus 1190, all divided by 2. Negative 120 is going to be correct as the correct answer to part A. All right. Very good. So we showed the units and we showed our work. Pretty simple. Then at part B, they're asking us to use a left Riemann sum with the 4 subintervals to estimate the total amount of water removed in the 8 hours that they were indicating for the time frame for which this tank data was taken. Okay, and then they're going to ask, is this an overestimate or underestimate of the total amount? And we need to explain why. Okay, so to begin with, given that this is a left Riemann sum, again we have 5 data points going across 0, 1, 3, 0, 1, 3, 6, and 8. But with this, we will only be using the left-hand sides for the heights for this problem. And so with that, we should be able to start looking at this to see what the total amount of water removed will look like. So our sum here is going to be equal to, again, because it's a Riemann sum at the left side, that means that it's going to be the area denoted as a base multiplied by a height. Again, because we're just adding up rectangles as we go across, the base multiplied by the height. And so with that, the summations will be as follows with a 1 minus 0, looking at the distance between the value of t multiplied by the left-hand height, which will be 1,340 for the first rectangle. So 1,340. And then with the next rectangle, coming across with the distance between 3 and 1. So that's 3 minus 1 multiplied by 1,190. And then with the next rectangle, distance between 3 and 6. So we take the subtraction of that, multiplied by the height of 950. And then the last rectangle between 6 and 8. and then the height of 740. Okay, so this is how we get the setup for the Riemann sum. Again, we have 4 rectangles coming across here, and with that, we will be able to look at the total amount of water removed during the 8 hours. So this is quite something that should be very easily done on the calculator. We just have to plug everything in here. So with the base of 1 on the first one, and then 1340 as the height, adding that with the next rectangle with the base of 2 and the height of 1190, shown right there. Then our third rectangle with a base of 3 and a height of 950, and lastly a base of 2 multiplied by a height of 740. So those are the 4 rectangles with the correct bases with each of their heights from the left hand side, and with that we get a total amount of 8,050. So 8,050, if I can write that properly, 8,050. But of course, unit wise, again, because we integrated for the liters per hour rate, but we integrated in accordance to time, that means we're back left with just liters again. Again, this is going to be of water removed, right, in the 8 hours. Okay, so this is the first part, but remembering that we still have a second part to answer for. They're asking if this is an overestimate or underestimate of the actual amount from this Riemann sum estimate. How we know, of course, is that if we take a look at the actual problem itself, as you can see, the R of t is decreasing all the way across the actual values here, right? So we can note that R of t, because we're going from 1340 all the way down to 700 continuously from those points. And so R of t is decreasing from that interval, so from 0 to t to 8. So during that entire time, because we're decreasing, and that means the left Riemann sum is an overestimate of the total amount of water removed. Okay, it should be fairly simple to visualize that, but in the case that if we really were to see it, keep a track that we're going from 1340 all the way down to 700. So if we were to take a look really quickly here, that if we had a decreasing function like this coming across, and we drew the rectangles again, we're doing the left Riemann sum. So if we went from the left side and we drew the rectangles from the points coming down, as you can see, the actual areas are above the line, because as the function is decreasing, we go across the base of the rectangle and take the area of the entirety from there. And so in this case, that drawing does show that it's going to be an overestimate because R of t was decreasing when we ran the Riemann sum. Okay, moving on to part C, they'll tell us to use your answer from part B to find an estimate of the total amount of water in the tank after 8 hours. Okay, so this is going to be a carryover from what we had. Of course, part B is going to be the amount removed from the tank, because it's going to be, right, this was the sum of R of t that we ran. Again, R of t, of course, was the water removed, while the problem did clearly state that we have W of t. So this equation, the 2000 times e raised to the negative t squared over 20, this guy is going to be the water added into the tank, right? And of course, the last piece of information is that 50,000 liters are at the tank to begin with at t is equal to 0. So looks like we have a lot of things to account for. Of course, the fact that we have to remind ourselves that we are going to integrate for 0 to 8, remembering that W of t, again, this is the water in. That's water coming into the tank. But then, of course, we have R of t, which is the water out. Right, D of t. But of course, remember, we have the plus 50,000 liters, because this was what we started with inside the tank as the problem stated. So this is how we get this set up here. We could use a little bit of integration rules for us to separate everything out so that we can run everything one at a time. So the w of t, because we don't know that one yet, is going to be subtracted by the same definite integral r of t. And then we're going to add the 50,000 after the fact. But of course, this is already part B done beforehand, right? Because we already did the integration estimation through a Riemann sum previously on part B. So all that needs to go into the calculator is going to be everything plugged in that sense. So we're going from 0 to 8. So w of t is going to be that 2,000 times e raised to the negative t squared over 20 dt. Okay, so that is wt plugged in for. But then we will subtract that from the actual r of t that we found earlier with that amount of 8,050 liters removed for the 8 hours. So 8,050 liters and plus the 50,000 that we had to begin with. Okay, so with that, we can run this all together on the calculator from here, and we will get our result. So making sure we plug this in properly, we are going to use the function integral. This is the Math 9 button on my TI-83 Plus. The function integral, we can run a definite integral of any sort of function. So it's going to be 2,000 times e raised to the, this is going to be the variable of t. Let's make sure we have the negative there as well. Let's insert in a negative. So it's negative t raised to the second power, all divided by 20. That's in the exponent. Then we're telling this calculator that we're integrating for the variable of t, now from the limits from 0 to 8 hours. Okay, then we can still plug in everything after the fact, after running this operation here. So we're adding the 8,000, well, no, we're subtracting the 8,050 because that's water removed during that time, and then we're adding the 50,000 to begin with for the tank. Okay, and so we get a total amount of 49,786, just nearest whole liter. Yep, so we just leave it at that. 49,786. Everything accounted and plugged in for the way that it should be for this problem. Pretty straightforward there. Okay, good. So let's go to part D here to finish this problem off here, so that it's going to tell us that for the interval going from 0 to 8 hours for t, they're asking, is there a time t when the rate at which water is pumped into the tank is the same as the rate at which water is removed from the tank. Okay, so this is quite interesting, right? So we're looking between here, they're asking to see, right? We're looking the rate at the water pumped into is the same as the rate at which water is removed, right? So between that entire distance here from 0 to 8, they're asking to see that is there a time where W of t is equal to R of t. Okay. One thing to note, of course, that because both these functions are continuous after we integrated them, is that for one is that we need to look, in my mind, is IVT, the intermediate value theorem. Okay. Usually, again, this is going to be looking at the way these continuous functions cross. For one, we know that R of t, the starting and ending, is that R of t starts at 1340 and it goes down to 700 based on the table, liters per hour, right? Our table shows that we are decreasing from that 1340 down to 700. So why don't we look at what WT starts and finishes at and see if they can at least confirm that there's going to be a crossing because these two functions are continuous. So what we can do is that we can simply plug in for it, knowing that we have 2,000 times the function of e raised to the, now we just do the negative 0 squared over 20, just keeping everything consistent. Again, we are plugging in for 0 into the w of t function, which is the 2,000 e raised to the t squared over 20. So by doing that, we can go and see what this is going to look like for us, which is obviously going to be a simple 2,000 to begin with, just making sure we had that in mind there. So it's 2,000, And then w of t will then go down 2 if we then pulled that function back and went all the way to the 8th hour mark. So the negative 8 squared all over that. So it's 81.524 if we ran 3 decimal places. Okay, so 81.524. Okay, so it looks like that's going to be the case, right? So think about this, right? If we had our two functions, right? So we had our w of t going from 2000 down to somewhere small like 80, right? So across the 8 hours, it goes really further down like this. While on the other hand, right, we have the smaller amount, so 1340 down to 700, right? So because we need to cross over to the 700 in a shorter amount of time, it will be guaranteed that they're going to cross thanks to the intermediate value theorem, confirming that both of these functions are continuous. Okay, so right, we can conclude that there is, according to IVT, and given that we know the starting and ending, that a t exists such that w of t will be equal to r of t. And because r of t starts at the lower point but ends higher than w, right? And they need to be inverted, right? Because w starts at 2000, r starts at 1340. R will be underneath, but once the 8 hours pass, w is down to 81, while r is at 700. Again, they will have to invert. Therefore, there must be a crossing for those two, confirming that there's going to be an actual crossing of the two paths. Okay? And that will be the case. Again, IVT has that covered for us. Pretty good. So, with that, let's go on to number 2, and we can go over those problems there, and then we can go over the answers to see how well we scored for these first two problems. So, problem number 2 is saying that for t being greater than or equal to 0, a particle moves along the x-axis. Okay, they're telling us that the velocity of the particle at time t is given by v of t being equal to 1 plus 2 times the sine of t squared over 2. Okay, then they're telling us that the particle is at position x is equal to 2 at t is equal to 4. Remembering that because we're going on a one-dimensional analysis here for a single particle, x is going to be the result of time being the independent variable moving across here. Okay, so with that, we can move on to part A here, where that they're asking that at the time is equal to 4, is the particle speeding up or slowing down? A great question indeed, as we are looking to make sure we understand the question about speed up and slow down. Right? Just as a quick reminder, speed up and slow down is not just the looking at velocity, it is a full analysis of both velocity and acceleration at the same time. So with that, if we want to know speed up here, again, speed up is going to be if velocity and acceleration, right, are both greater than 0 or less than 0, right? They both need to be the same sign, both positive or negative. While on the other hand, so v of t and a of t, opposite signs, right? So if they're same sign, that's going to be speed up. And in the other two cases where one is positive and the other is going to be negative, this is going to be a slow down. Okay, so with that, looks like we need to account for the acceleration equation because we only have velocity at time is equal to 4. Of course, we draw the fact here that acceleration is going to be the velocity equation taken one derivative with respect to t. So with that, we can run the first derivative of the velocity as the 2 times the cosine of t squared over 2 and multiply by 2t over 2 as a result of the chain rule coming out for that graph. The 2's will cancel out, so it's, to clean it up, is just 2 times t times the cosine of t squared over 2. Okay. Then with that, we can go look at both the velocity at the time of 4 and the acceleration at the time of 4 for both of those functions. This is still a calculator section, so we can go and use our calculator to then determine both of these. So velocity is going to be the 1 plus 2 times the sine of, again, plugging everything, it's t squared over 4. It's going to be 4 squared over 2. Okay. This is going to be 2.979 if we round it to the third decimal place. But on the other hand, we can also on the same time here do the acceleration. So it's 2 times 4 times cosine, again plugging in 4 for time. And then it's going to be 16 over 2. And that's negative 1.164. Okay. So with that, we get the 2.979, and then this will be negative 1.164. Okay, so as you can see, with one being negative on the acceleration and the velocity being positive, right, these are different signs, so therefore this is going to be a slow down at the time is equal to 4. And our work does show that we understand that with one being negative and the other being positive, that results in the particle slowing down because the change there that we've noticed in our analysis. Okay, let's go to part B here, so that they're going to tell us to find all times in the interval going from 0 to t to 3 when the particle changes direction. Okay, so in this case, right, if we're looking for a change in direction, that means that we need to look at velocity and looking for a change of sign, right? So if we take the velocity and this is going to be a direction change, means that there's a change in sign. That means that we can graph this directly and take a look if we are going to cross the x-axis, right? Obviously, if the x-axis means that the y value is 0, we're looking to change in positive and negative as we cross that axis itself. Okay. So let's make sure we can show this so that for this graph, we can clear this out. So to begin with, we're going to graph the velocity equation, the 1 plus 2 times sine of t squared over 2. So let's go ahead and do that. 1 plus 2 times sine of, we have to swap it to x because we're graphing on the xy plane, x squared over 2. And making sure in our window, we're setting it 1 to, maybe negative 1 to positive 4 will show us everything. Negative 1 to positive 1 should be good enough. We're just looking for the crosses here. So with that, we can go and, so there you go. So between those two, we can look at those crossings from the graph to then look to see what we can find from there. So we can look at some zeros that we can calculate by tracing it across. So by coming around here, there you go. So we want to go to the left side of this graph. Okay, so the left side before we cross the axis, then on the right side afterwards, the calculator will zero that in and we get 2.707 if we round that off properly. That's within our time interval. So at x is equal to 2.707. Again, this is a crossing from positive to the negative direction, right? And then let's go one more time on tracing another 0. This time going from the left side here on this intersection, going over to the right side. And if you look at that, that's the point at 3.394 if we do that, right? So 3.394. Unfortunately though, if you look back at the directions here, is that it is outside of the interval. We're only going from 0 to 3, cutting it off there. So because this is outside, this is going to be no good for us to actually look at. There's only one time, right? So at t is equal to 2.707, the particle changes from As you can see, right, as we took the note, it's from the positive to the negative direction. So the positive direction to negative. Right? So this write-up of an answer should be good enough for us to mark everything that we need to know for that time interval. Again, we were looking at the graph of the velocity from our calculator to then look at those actual intersections and find the times in which that would be the case when that particle changes direction. Okay, good. So with that, we can go on to part C here. And then we're going to tell us next that we want to find the position of the particle at the time is equal to 0. Okay, so we have a couple of ways of trying to solve this guy, and which one, of course, is that because we're only given the velocity equation, right, that they started out before right there, because we're only given velocity, we if we're looking to get position, which is x of t, this is going to be the integral. This time, right, we can do indefinite or definite, either would work, but in this case, I think definite will be better because we know that we're looking for 0, but we're also looking for, and what we have is that we have the time at 4, we have a specific position as well. So with this, we can go and use our good old friend if we integrate v of t between those two limits. That thanks to the fundamental theorem of calculus, FTC, because we're taking a definite integral of velocity, that's going to be the difference of the position at 4 and the position of 0. Right? So if you're looking to isolate everything and making sure we have everything ready for our calculators here, is that we can move back the x of 0 and isolate that. So x of 0 then is going to be x of 4, which we already know, subtracted by that definite integral of v of t dt. Okay. A little bit of algebraic movement from the fundamental theorem that we know beforehand. Then we just plug everything in with x of 4, right? At the time of 4, the position is going to be 2. Subtracted by the definite integral from 0 to 4 of 1 plus 2 times the sine of t squared over 2 dt. Right? This will all then go right into our calculators, and then we can look for, with this isolated of x of 0 from that. Okay, so we show that through our calculator work right here. So it's 2 minus the function integral of what we have inside. So it's 1 plus 2 times the sine of, this is going to be t to the second power over 2. Okay, and with that, we're going to tell this calculate that we're going for the variable of t from the interval from 0 to 4 on time. And so we can run this through, and we get the total amount of negative 3.815. Okay, again, this is going to be the position at 0. This is fine. Again, position can be negative. It's just where we're placed before the 0 mark. So everything does check out. We use fundamental theorem to then find the exact position at time of 0 for this particle. All right, so let's go to part D here, that they're going to ask to find the total distance the particle travels from the time of 0 to time of 3. Okay? Total distance, of course, meaning that we have to bring up through our memory the equation of that, right? Because net distance, just the final, as you can see, right, from what we actually did beforehand, is just one minus the other. If you want total distance of having no regard about the signs overall, total distance, of course, is going to be the, if you want to write this out, right, so total distance is going to be actually the integral, but this time, because we go from 0 to 3, it's the absolute value of the velocity equation respect to time, right? Again, absolute value meaning that the negatives don't matter. They will not cancel out with the positive distances. We just add them all up without any regard for the sign. So with that, we just have to plug that in directly into our calculators. So by going from the absolute value of 1 plus 2 times the sine of t squared over 2 and the absolute value dt, with this, we can then find the total distance that this particle traveled from the 0 to 3 mark. Okay? So with that, we just run again the function integral, but this time we need to make sure that we run in the absolute value, right? ABS, the absolute value now of the function in there. So it's 1 plus 2 times the sine of t to the second power over 2. Okay. So with this, we close the sign off, we close the absolute value off, then we tell this once more that this is for the variable of t, this time just from 0 to 3 instead, making sure all our parentheses are lined up. It'll take a second for it to then flip over the graph as it calculates this along, and we should be getting a complete answer in just a second here of 5.301 if we round it to the third decimal place. All right. Total distance is 5.301. A simple test, if we do remember how to find total distance in regard to just net distance of the difference between 2 points. Again, total distance means that you have to do the absolute value of the velocity in the integral. Okay. So I think with that concludes it for number 2. So that's all 4 parts. So with that, we can go back to problem number 1 and we can start correcting our work. And we correct usually 2 at a time as we go across the total 6 problems on this free response section. So we can move this over to our answers here. So I do have here on this side, if we can line everything up here, that we have the 2016 scoring guidelines. Again, we just go through this once we complete 2 problems at a time, making sure I show with my making sure we get the right color here so we can highlight what we are looking at here. So yes, we are going at question number 1 here, and we are looking once more at the pumping of water in the tank with that table shown across there, right? And we have the equation W of t of raised to the negative t squared over 20. So at part A, because we were estimating r prime of 2, right, we needed to go use, as they shown right here, the average rate of change. So this exact equation of r of 3 minus r of 1 over 3 minus 1. And again, this indeed with the amount of the actual units coming up, 120 liters per hour squared. That does check out exactly. So with the right form of the estimation and our work coming together here is that we get 2 out of 2 correct for part A. And both the setup and the actual answer with the units are correct. Then at part B, again, they were talking about using the left Riemann sum with 4 to find that estimation if we are looking at an over or under estimate, right? As shown right there, right? We boxed it over here, the over or under estimate of that value after we take the Riemann sum. So as shown, of course, we have here the bases multiplied by each of the heights in that line of work in the answer key. This is the 1 times 1340, 2 times 1190, 3 times 950, 2 times 740. All that adds up to 8,050 liters of water removed in sum of R of t, the amount of water removed from the tank. And with that, they also did state that because we are decreasing on R, it's going to be an overestimate. And before, a bit of a sketch to show that for any decreasing function, that if you took the left Riemann sum, so the left-hand heights, and moved it across for the side, it's going to be an overestimate of those values. Actual answer and the estimation as well as our work, and on top of our third point here with the overestimation as our result, we get all 3 out of 3 correct for part B. Pretty nice. Okay. Then going down to part C here is that they were looking to see what the total amount of water was going to look like. 1,000 to begin with, right? That we started with in tank, and then it's 0 to 8 on the W of t, and then subtracted by R of t, which we found earlier on part B here at the 8,050. So by running that integration through, we do get the correct amount of 49,786 liters. And the answer is exactly correct the way that it should be for part C. Okay. And lastly, on part D here, they're looking to see if we can confirm that W and R will be equal to each other at any given time. And because we can see that the actual difference between the two, right, would actually lead to them crossing each other eventually with the intermediate value theorem, right, the one that I pointed out in my answer right there, right, according to IVT, abbreviated as intermediate value theorem. Okay. It will confirm in which that W of t will equal to R of t at one point in time between the 8 hours. Okay, so both the setup, again, the answer is both correct, so that's 2 out of 2 correct for part D. Pretty nice that we've done everything pretty well for this first question right here. So that gives us for question number 1 in our record right here that it's going to be 9 out of 9 for the first question. And let's move on to the second one before we go to the non-calculator section of this exam. Okay, so question number 2 here, and we're dealing with that particle moving along the axis, right? So they give us that velocity equation of the v of t right there. And the first question is asking for that time of 4. They're looking to see if it's speeding up or slowing down. Of course, they do show in the answer key that we need to look at both the velocity and the derivative velocity, and that's going to be acceleration at those 2 points, right? So for us, right, we did show that the velocity at 4 is a 2.978. That does match up. And then the negative 1.164 on the derivative velocity, again, this is going to be acceleration as shown back there, right? So because of that, it is going to be a slowdown at time is equal to 4. Right. Our conclusion and setup are both correct, giving us 2 out of 2 correct on part A. Okay. Then moving on to part B here is that they're asking the time in which the particle changes direction. Right. So as we can see, when we did our graph, we did conclude one time that 2.707, the 3.394 on our graph was outside of the 0 to 3 interval in which we were looking at. So in that case, because 2.707 was the only time in which we crossed from the positive to the negative side for this graph on the velocity, we only have one change from the positive to negative direction as we shown on there. So with the answer shown and our reasoning, we both get 2 out of 2 correct for part B. Okay. Then onwards to part C here is that they're asking the position at time of 0. Just like what they did right here is that they set up the fundamental theorem so that x of 0 is going to be moved, and they flipped the limits on the answer key. In any case, subtracting it is exactly the same setup anyways. They just did a little bit of limit, the limit manipulation there, but nonetheless, though, flipping the limits and slapping a negative coefficient is exactly the same, because the answer of negative 3.815, there is a negative sign that might be kind of hard to see on this stream here, but the negative 3.815 is exactly correct right there. And so because we had the integral setup as well as the condition of x of 4 being 2 as what they stated at the start of the problem, that is all 3 out of 3 correct for us, matching exactly what they wanted to see work-wise to get the fundamental theorem all set up here. Okay. Lastly here, that they're looking for the total distance from 0 to 3. Of course, that meant we had to take the absolute value of the velocity equation. By doing that, we get 5.301. Right? The integration, making sure we set up inside the absolute value for the velocity equation, then getting the result that we're looking for will give us 2 out of 2 correct on that part. Okay. Very good. So looks like for question number 2 as well, we are 9 out of 9 on that. Very good. So looks like we are well on our way to scoring pretty alright on this problem. So something to note before we continue is that question number 3 and onwards, right, this is going to be, for the rest of this, right, this is the no calculator section. We'll still copy down the problem and any other graphs onto our notebook, but for the rest of this exam, our trusty TA83 Plus graphing calculator is going to be put away and no longer in use for the rest of this exam. Okay, so let's go ahead and move on back to what we have to begin with here. Going with question number 3, and we'll do 3 and 4 together before we go and correct those 2 problems. So question number 3 is that we have ourselves a graph here. Let's see if I can show this properly. So we're going across 4 and 12. We go by 2s, it looks like. So we go across here. Okay. So you go 2 and 2 right there. So negative 2, negative 4 on that part of the graph. Okay. Then we go up there for 4 and down there for negative 4. Okay. Then we go 2, 4, 6, 8, 10, and 12 right there. Okay. Going across the positive x values like there. Okay. And we can start graphing. So negative 4 comma negative 4, negative 2 comma 0, 0 comma 4, 2 comma 0, 4 comma 4, 6 comma 0, 8 comma negative 4, 10 comma 0, and 12 comma negative 4. Okay, so we are going to go across like this, all the way down like this, up and down like this. Okay, that's the main idea for the graph on problem number 3. And they're telling us that this is the graph of f shown right there. So in this case, it tells us that they tell us as well that for the interval from -4 to x to 12, function g is defined by g of x being equal to the integral from 2 to x of f of t dt. Okay, so that is listed out right there. Okay, then at part A, they're asking, does g have a relative minimum, maximum, or neither at x is equal to 10. Okay, and we need to show our work as to such. Okay, because function g is being asked for relative minimum or maximum, that must mean that we must look at g prime of x and look to see that's at 0. Again, in this case, it's going to be g prime of 10 being equal to 0. But of course, we have g listed out as the integral of f. So if we take the first derivative of g, that also means that we are doing by deriving the definite integral thanks to fundamental theorem. This means that we are looking at f of 10 for that result. Okay, so as you can see, right, f of 10 in this case is indeed on the graph, and that is indeed equal to 0. But, right, this is where a big but comes in. Right, the issue is that at f of 10, if we do a little number line analysis, because we need to see if it's a minimum or maximum, right? So at 10 of g prime of x, we need to see if it changes the sign coming across that 0. In our case, right, as you can see, leading up to 10, right, the graph of f or g prime is negative, hits the 0 at 10, and goes negative again. So it's negative on both sides of the point at 10. Right? So because it doesn't change sign, it is neither a minimum or maximum, so we need to show that, right? So g of x does not, well, maybe the better wording is that has neither a minimum or maximum at the time is equal to 10, right? Again, as we can see from our work, because it doesn't change sign. Right? Because g prime of x is negative before and after t is equal to 10. Okay? So we need to look at the change of a sign, not keeping the same sign at negative. So with that, we can conclude that is neither a minimum or maximum for that graph. Okay, good. So part B, they're asking then that does the graph of g have a point of inflection at x is equal to 4. Okay, now we're cranking this up another notch here, because a point of inflection means that we are looking at the g double prime of x. In this case, because we know g prime is equal to f of x, that's going to be f prime of x in that sense. Okay, so looking at g double prime of 4, we need to see if it looks, in that case, to be equal to 0. And as you can see, right, at 4, there indeed is going to be, right, 0 on that sense, because f is already on a corner right there, meaning that it is it does not have a slope there at 4. So because of this, right, if we look at this as well, that at the g double prime of x mark at 4, looking at the graph of f, right, so because g double prime of f was already in our relationship as f prime of f, that means that we're looking at the slope of f leading up to 4. So everything before 4 is all positive because we're increasing into 4, and then right afterwards you go negative after the fact. So it looks like here, this is going to be yes. The graph of g has a point of inflection at x is equal to 4, right, with g double prime of x being positive before, oh sorry, it's a t, this t is equal to 4, before t is equal to 4, and, oh, this, it is x, well, what am I doing? So x is equal to 4 and negative after x is equal to 4. Okay. Good. So we can have all that set up right there. And again, our work shows accordingly with our number line analysis for that. Okay. Going on to part C, they're telling us to find the absolute minimum value and absolute maximum of g on the interval -4 x go and 12. Okay, so with this next step here asking about absolute minimums and absolute maximums, we now have to take a look to see on the possible, what I like to say, the candidates for some possible answers for this problem here. Okay, so our candidates, of course, will include the actual endpoints. So x is equal, or yeah, x is equal to -4 and x is equal to +12, as well as any local mins or maxes. Okay, so again, we have the endpoints because those could be where the function ends and that ends up at the highest or lowest point, as well as any local minimums or maximums, which are defined, of course, at the first derivative being equal to 0 and we are crossing the x-axis. Okay, so in that, because it's g prime, that's going to be f of x, right, crossing the x-axis, and looks like we have about a couple of points here. See, at -2, we're crossing from negative to positive on f, and then at 6 from positive to negative. We'll always remember the relationship that f is same as g prime of x. So in this case, at x is equal to -2, in this case, because we're going from negative to positive, that's going to be a local minimum. And then on the other side, at x equals +6, right? Because we're going from positive to negative, crossing the 6 there, that's going to be a local maximum. Okay. So we have these three candidates to look at, and so now we need to plug them into our g of x function to take a look, right? So at x is equal to, so we can make a table actually as well. So we have x and then g of x. Okay, so at the points -4, -2, 6, and 12. Okay, so at x is equal to, so g of -4 is going to be the integral from +2 to -4 f of t dt. Again, taken directly from the start of the problem here with the equation of g listed out for us. And as you can notice, we have here inverse limits because we have the higher number on the bottom, lower number on top. So we're going to swap that around for the sake of our calculations here. A negative coefficient from -4 to +2, f of t dt. So going from -4 to +2, right, we have all of this to come across, which means we need to go around here and take the area underneath there and take the area over there, which, as you can see, with the area underneath the curve defined as two triangles, one underneath the curve and one above the curve. So with two triangles listed out, we're going to need to keep the negative coefficient there, cannot forget about that. But with the first triangle, with 1/2 base times height as the standard equation, the first triangle is underneath, right, with a -1/2, right, well, so we can leave it +1/2. The base from -4 to -2 is 2. And the height, again, going from -4 all the way to 0, we can leave this as a negative height because we are underneath the curve when we're calculating that area. Okay. And then we add that up with the next triangle from -2 to +2, so the base is going to be 4. That's 1/2, a base of 4, and the height will be 4 as well because the peak of that triangle is at 4. Okay. So with all that listed out there, we are going to get a negative, this is a -8 times 1/2, so it's -4, and then 4 times 4 is going to be a positive 16, but divided by 2 makes it a positive 8. So with this is a positive 4 with a negative coefficient waiting for us. That's negative 4 as a result of x of negative 4. Then going forth, we have g of negative 2. So we do the same exact thing. This time here, which is going to be 2 to negative 2 f of t dt. Which, in our case, we need to swap this around again. From positive to negative 2, keeping a negative coefficient there because we need to go from lower to higher on our limits of the integration. Now, thankfully, because negative 2 to positive 2 was already figured out by us earlier, we just need to go with this guy here, right? Because that was our second triangle from negative 2 to positive 2. So with that, we just keep the negative there. And it's going to be 1/2 times 4 times 4 with one triangle taking the area of during that time, which is going to be a negative 8 as a result. Pretty nice. Then g of 6. Again, we can leave everything alone because it's 2 to 6 now f of t dt when plugging everything in. Okay, so now we have another triangle to go from 2 to 6. Right? Again, all this is above the x-axis as we go across. From 2 to 6, we have a base of 4 and a height of 4 coming from the top there. So with this is going to be 1/2. Again, base of 4, height of 4, all positive, giving us positive 8 right there. And lastly, g of 12 goes from 2 to 12, f of t dt. Okay, so we have 2 to 6 already part of it right there, but we have a few more negative triangles to account for. One full triangle right there and another one right there. Okay, so we have here one triangle with a base of 4 and a height of negative 4, another base of 2 and a height of negative 4 right there as well. So we just keep all that in mind. We can leave the positive 8 from the previous, going from 2 to 6, but then now we need to add with the 1/2. Again, base of 4, height of negative 4, and another 1/2, base of 4, height of negative, height of negative 4, base of positive 2, as you go from 10 to 12 for that other triangle underneath the axis. Of course, making sure that the negative heights are accounted for. The 8 and this is going to be negative 8, so those two will cancel, leaving us with just a negative 4 left after those canceled. Okay. So what that looks like, we have all of our candidates all sorted out, and it looks like we have our winners for the maximum and the minimum for these two functions. Oh, sorry, this one function, the two max and min values right there. Okay, so g has a maximum at the g of 6 being equal to 8 and minimum at g of negative 2 being equal to negative 8. And with that, we have our points all sorted out, our work showing for us how to find all those areas using integration and fundamental theorem underneath the curve. Okay. Lastly, let's see if we can finish off part D here, where it says that for the interval from negative 4 to x to 12, find all intervals for which g of x is less than or equal to 0. Okay, so once more, we're looking for some values for g, of course remembering that g prime of x is equal to f of x for the case of, wait, that's not important, sorry, g of x in this case is still the integral from 2 to t f of t dt. Okay, let's go back to our original equation here. That's the wrong relationship, but this is the right one. So g of x is equal to that integral. Okay, so if we're less than or equal to 0 from here, right, what we can obviously note is that we can just start doing a little bit of symmetry here to match where we're going to be less than or underneath 0. As you can see, from negative 4 to 2, this is all negative area right there. And we can match that symmetrically up to the point of 0, right, where that same area is matched on this side. So again, because it cuts off 0 at the point of 0 for the area underneath f, right, we can do the first interval from negative 4 to 0 for the first part. And, right, we can go forward. So this is all positives and this is all negatives, which actually at the very last point here, right, because we have this full triangle canceling out with this full triangle, again symmetrically from the way that these segments have been lined up, we lastly have just this 1/2 triangle here and that half right triangle right there as well, right? So everything cancels out exactly to 0, going all the way to the end there. But I think one thing that we're kind of forgetting though is that we're not looking exactly for just the graph of f. We need to look at it in the face of going from 2 to f of t, 2 to f of t dt. Yeah. Okay. So I think with that, because we were doing an inversion up until that point, everything would be 0 until the point of 2, right? So again, remember, because we've inverted everything underneath because of that, and we have all those negatives out there in front of us, right? Everything would have been 0 from -4 to +2, because that's where our integral begins for f of t dt, okay? And we go forward from there, right? So from 2 onwards, we have, because we integrate starting from 2 as the hard cutoff, going onwards with the full triangles, one on top, one on bottom. Then looks like starting from 10 to 12, we have another section that's underneath, again, with the hard cutoff at 2, with the positive triangle, negative triangle, and we go a little bit further after that. So we can note that g of x is less than or equal to 0 from the entire points from -4 all the way to +2. And the next interval, again, was when we start being negative again after canceling out with the one positive at 2, all the way from 10 to 12. So with that, looks like we have everything all sorted out right here for us. Okay, so that looks like it's a pretty okay deal for us. That will finish off problem number 3, and we can move on to problem number 4. Okay. Still just a little bit of geometric analysis there for problem number 3, but with that, we are good for problem number 4 here. It's going to tell us the differential equation dy over dx is equal to y squared over x minus 1. Okay. Now part A, which is going to be a slope field question, will be on the packet, which we will look over here together. Okay. So we have here, right here, that on this packet, they're asking us to sketch the slope field graph, right, with the 6 points indicated for this guy right here. So we can make a table because there's only 6 points, right? So in this case, it's going to be x, y, and then the slope dy over dx for each of those points, because it's a whole equation. So we have the point at x is equal to 0, going all the way down for 3 points, because we can go up those 3 y values of 0, 1, and 2. Then continuing forth, we have 3 more points at x is equal to 1. Right, so, oh, sorry, it's 2. X of 2, right, going up those 3 points right there. So that's going to be same y values of 0, 1, and 2 for all 6 of those points accounted for. And now we just plug them directly into the actual equation for us to find the slopes of them. So with 0, 0, we get the result of 0 over 0 minus 1, which gives us 0. Then 0, 1 is going to be 1 squared over 0 minus 1, giving -1. And 0, 2 will give us 2 squared over 0 minus 1, giving us -4 as a result. Okay. Then at the next point at x being 2, so it's 2, 0, giving us 0 over 2 minus 1, giving us 0 right there. And then 2, 1, so it's going to be 1 squared over 2 minus 1, giving us +1. And then 2, 2, giving us the 4 over 2 minus 1, giving us +4 as a result. Okay, not so bad on that side. So now we just need to go over each of those points and start ticking off the slope field. So they have 0 slope on that one. The 0, 1 is a -1 slope going downwards this way. And then -4, so a very steep negative slope right there. Then at the next one at 2, 0, we have 0 again right there. Then a +1 right there, and then a +4, a steep positive slope right there. Okay, I think that all matches up what they were asking for all 6 of those points. Again, just a bit of an exercise to plug in both the x and y coordinate into that equation for us to then solve for those slopes. Okay, so that was already part A. Part B then is asking is that let y be equal to f of x, okay, be the particular solution to the differential equation. With initial condition the f of 2 is equal to 3. Okay? And then we want to write an equation for the line tangent to the graph of y is equal to f of x at the x is equal to 2. Okay, then use that equation to approximate f of 2.1. All right, so quite a few steps here, but nonetheless, just a few things we need to point out here before we actually begin here is that they're telling us that we have the particular solution, again, y is equal to f of x, with the initial condition f of 2 of 3. So we need to write that equation out for this. Okay, let me make sure we actually set our volume properly for this. Okay. So with that, we're looking to make sure that, again, that for this we can get a line tangent at that point of 2, 3, and then we will approximate f of 2.1. Okay, which in this case, because we're doing a tangent line, that means, right, so the tangent line equation, this equation will then be, again, usually best in this point slope form, y equals mx minus h plus k on the outside right there. Okay, which of course h comma k in this case is our 2, 3, with the point that they gave us right there. And in our case, m is going to be dy over dx evaluated at the point 2, 3 for us, right? And we need to know the slope at that specific point of 2, 3, and we will need to plug those two coordinates right into the dy over dx equation. So with that, we get 3 squared on the y, and then 2 minus 1, okay, giving us 9 over 1, giving us a slope of 9 at exactly that point. Good, so we can go ahead and put everything together here. So y is equal to 9 of x minus h, so it's minus 2, plus k is a plus 3 on the outside. Okay, so this is going to be our tangent line equation listed out for us. But as well, our next part is that we have to approximate for f of 2.1. So now with an approximation using this tangent line, we can then plug this in. So f of 2.1 will then be plugging in 2.1 into the x right there, which will give us 9 times 0.1 plus 3, which gives us 3.9 as a result of that approximation of f of 2.1. Okay, pretty simple, just to go back to our previous equation that we just made to then do a quick approximation for this question here. Okay, that's pretty good. So that will leave it for part B here. Then they're going to ask us on part C to actually find the particular solution. So this solution of y is equal to f of x, okay, with initial condition, the same one that they gave us in part B, this is going to be f of 2 being equal to 3. Remember, this is the actual point 2, 3 on the graph of f of x. So let's get this show on the road here. So again, the differential equation dy over dx is y squared over x minus 1, meaning that we have to go and do what they want to see as the separation of variables. Right? Because we need to make sure all the x's go to the side of x, all the y's go back down with the side of y's, so that we can integrate both sides of the equation. Very important, you will actually score no points on this problem if you do not do this step of separating out the variables before integrating. So with that, we just need to set this up as dy over y squared with some division, and then with some multiplication of dx over x minus 1 like that. Okay, very simple algebra, but that also means that now we're ready, because the variables are separated to their appropriate side, to then run the indefinite integrals on both sides of this equation, meaning that with y of y squared, again, this is going to be basically the y of negative 2 power, meaning we have a negative y to the negative 1 power to then get that negative 2 in the derivative. Then running that, this is going to be the natural log of the absolute value of x minus 1 plus c as a result. Remember, that plus c is very important to result from indefinite integration on that side. So with that, we ran the integral, but also then we need to then solve for c using our initial point. Right? So by solving for c, we plug everything in. So there's negative, then 3 on the inside, negative 1 power is equal to natural log of 2 minus 1 plus c. So with this is going to be negative 1/3 following the exponent first. Then the natural log of 1 is going to be 0 plus c. Very simple rules of logarithms there. So with that, we have our c being equal to negative 1/3. Okay. Then we can go back and then isolate for y. So this is negative 1 over y if we want to kick it out of the exponent right there. The natural log of the absolute value of x minus 1 minus a 1/3. Okay. Then by throwing everything in the negative to cancel out, we have negative natural log of x minus 1 plus a 1/3. And then by flipping everything over, y is equal to 1 over the negative natural log of x minus 1 plus 1 over 3 on the denominator. Okay, so with that, we have everything set up for us here as y being equal to f of x now completely on its own. Okay, that does not seem so bad at all. Just a few lines of work here to do this type of separation of variables. But with that, we should be good to then correct questions 3 and 4 for us to see how we're doing score-wise on this exam. So let's go ahead and swap back over on this side, right? So we're going back to our answer key here, starting at question number 3. So I'm moving down here. We have question number 3 that we're going to pick up from. So again, we have that graph of f right there, and we're doing the relation between f and g being that definite integral from 2 to x f of t dt. Okay, so because of this, right, we're looking to see if we have the relative minimum at the specific point, right, at 10. So relative minimum or maximum at x is equal to 10. In our case, it's going to be neither, as shown on our answer here, right? Because, right, is that we, because we're just going to be stuck at less than 0 for the entire interval, right? Again, we're stuck at negative for both sides of the positive 10 on the x. So with that, that's going to be a 1 out of 1 correct for part A. Okay. Then part B is that they're asking if we have the point of inflection at x is equal to 4. So because of that, right, with a point of inflection, right, because we're looking for the change of increase to decrease for that, again, meaning that we have to do the second derivative of g as we come across. I see we went from positive to negative as shown in our work right there, right? So we did confirm that as a point of inflection right there. That's 1 out of 1 correct for part B. Okay. Then for part C, we are looking for the absolute minimum maximum, and our candidates are all there. So negative 4, negative 2, 6, and 12. Again, all those points were going to be correct because of that. Then by running that through, our actual answer is that g of 2 is negative 8, right there as a minimum, and g of 6 is positive 8 as a maximum. All those line up exactly with our work on having to follow up with our answers there. So with that, that is 4 out of 4 correct for part C. Remembering that we had to follow along with fundamental theorem, going down each of those points as he picked out those candidates for some maximums and minimums. Then lastly, for part D here, is that we have the intervals from negative 4 to positive 2 and 10 to 12. Okay. Ooh, I think something is actually happening on the other side. So I might need to step out here for just a few minutes here. Again, we'll just give this a be right back sign right here. And Sorry, there is something that had to be attended to for just a second. Ah, yes, I know that viewer Nod does want me to return as quickly as possible, so we had to make sure we should be good to finish up our corrections here for question number 4 now, because we were dealing with that. Okay, so we just finished all the intervals in which we were underneath 0 for g of x, right? They were looking at that for these intervals because, again, we had to measure the actual areas underneath the actual equations. Again, with the parts in which us being underneath 0 from -4 all the way to +2, and then 10 to 12 because we started our integration. Oh, what is happening here? We started our integration at the, if we want to get rid of, okay, because we started integration at x is equal to 2 because of what we started out as a rule for g of x. So because of that, we inverted the entirety of -4 to -2. And then because of that, we then went back negative again from 10 to 12. Okay. Yes, Claire does greet us with 4 eyes. Yes, thank you. Wow. But yes, it's been a long time since someone has ever called me that, but that is indeed a test to see how old people are, because 4 eyes is only a comment used for people back then. But nonetheless, though, that completes question number 3's corrections at 9 out of 9 correct right there. And we should move on to question number 4. Of course, it'll be great if my returning viewers, can hit the like on the stream so that I can be pushed up on the algorithm, that they are a part of the stream. Am I calling Claire old? Maybe, but maybe also that I'm nearly just as old, and 4 eyes is simply a term not used so much anymore and wears glasses. But nonetheless, though, we can go on down to question number 4 now, where we have the differential equation set up here. Right at the start. Again, part A was going to be done on the packet because we were dealing with the slope field, and our work does show as follows. All right, they want to make sure that we had the 2, 0, so that is going to be correct on the first part because both of those do match exactly what we have on the packet. Then the non-zero slopes at the negative they wanted to on those 2 points, and then +1 and +4 on those points as well, showing exactly what they need to. Very good. So that filled out for us. Okay. Then on part B, they're asking to see that we have the particular solution, but we want to write the tangent line equation at the specific point at 2, 3, and then we approximate 2.1 after the fact. Right. So if you wanted to find the actual slope, right, we had to take that differential equation, plug it in, and get a 9 as a result. Exactly what we had as we plugged in the point 2, 3 into that line of work right there. And then by setting up the equation of y is equal to 9x minus 2 plus 3 on the outside as the point slope form dictates, we get the approximation of 3.9 all set up the way that it should be on this exam paper. Okay, so with that, that is going to be 2 out of 2 correct right there. All right, and lastly, we are looking for the part C here, which is going to be the particular solution, which of course, as they show right here, that's a separation of variables as needed. And of course, with this note here that you will get no points if you do not do separation of variables as needed for this part of the exam. I wrote that down myself, of course, as being experienced with having to solve these types of problems. But with that, we move forward to make sure that we follow that we separate this one, all shown exactly in that step. Running the integral, so it gives us a -1 over y is equal to the natural log of the absolute value of x minus 1 plus c, as shown right there. We solve for c, giving us -1/3 as a result because of that, right, by plugging in for the actual values for the point 2, 3. Then lastly, for solving for y in the end, it gives us a 1 over the negative natural log x minus 1 over, right, so 1 over, the negative natural log x minus 1 and a +1/3 at the end of that. Okay, so with that solution, again, everything checks out in terms of our lines of work, exactly where they want to show them. Just a little bit of a rearrangement at the very last line there. Everything else matches up, so that's going to be 5 out of 5 correct for this problem. Pretty good. So with that, that will leave us with question number 4 also being 9 out of 9. Okay. So with that, we should be good then to move on lastly to the last section here, questions 5 and 6, as we clear up this exam. Okay. Desk camera to then go ahead and get ready for the next part right here. Okay. as we go to question number 5. Okay, so question number 5 then tells us that we have, just as a little sketch here, we have looks like a funnel right here, okay, which we have the changing R radius and the height of a sort of liquid that's going to be pouring out of that funnel. So they're going to tell us here that the inside of the funnel of a funnel of a height of 10 inches has a circular cross section shown in the figure. Okay, so then they tell us that at height h, the radius is given by this equation: r is equal to 1 over 20 multiplied by 3 plus h squared. Okay, and they're telling us where we go from 0 to h to 10. Okay, and they're all going to be in inches for what we're dealing with in terms of these units. All right, so that's the context right there. So at part A, they're telling us to find the average value of the radius in the funnel. Okay, good. So average value once more, they're looking to pester us with that again, which means we need to set up the average value equation, of course, given that we're dealing with a radius. Average value, of course, going to be is equal to 1 over, then as a coefficient of the actual radius itself between the 0 to 10 limits. So it's 10 minus 0 for the definite integral from 0 to 10 for that radius function, which is going to be 1 over 20 multiplied by 3 plus h squared dh. Okay, right. By plugging that all in, again, keeping the fact that this is the radius function in respect to height, we can then solve for this using some nice integration by hand, and we can get through this here. So this 1 over 10, then we can multiply the 1 over 20 coefficient, just kicking that straight out of there with coefficient rule of integration. Then we're left with 3 plus h squared in the integral, which gives us 3h plus h cubed over 3 evaluated from 0 to 10. Okay. With 10 times 20, we get 1 over 200 as a coefficient waiting for us as we evaluate this. 10 coming down from the limits there, which is going to give us 3 times 10 plus 10 to the third over 3. Okay. Then subtracted by 0, because 0 is coming across for both of these, will end us with 0 as a result. Then keeping everything else intact here, this is going to be the 30 plus 8,000, because 10 cubed is 1,000 over 3. Okay, we have a little bit of back and forth with these coefficients, but I think we should be fine for it, given that 30 will easily be taken into, this is going to be 90 over 3, and we just multiply across afterwards, so this is going to be 1,090 over there's 200 times 3, so it's 600. With that, we can cancel out 1 0. 109 is not, is that even, I think that's prime altogether. So with that, 109 over 60 is going to be the result of this average. So this can be inches because it's average of the radius. Okay, we leave it just like that. Non-calculator, no need to go any further with the decimals. That should be just fine for what we're doing here. Okay, then they want to then at part B find the volume of the funnel. Right? If in this case, because we're doing a cylinder here, even though it looks like a cone, it's overall cylinder because it's a funnel. It doesn't end on a point here. So that in case we're doing volume, again, this is going to be the pi r squared times h. Of course, the issue is that r is not a singular number and h goes entirely from 0 to 10. Right? So what we can do here instead, right, because this is just going to be for a flat cylinder, what we're going to be doing here is that it's going to be the integral, because we're doing this in respect to the height, going from 0 to 10 of pi on the outside r squared, like this. Okay, again, that's just the way that we can set this up as we add up all the radii that is going up the heights from 0 to 10, keeping track of our volume equation right here. So with that, we have pi times the definite integral from 0 to 10 for the radius squared, which is going to be all of 1 over 20 times 3 plus h squared, all of that squared dh. Okay. So with this, we just need to start cleaning this up inside of the integral before we run it through. This will be 1 over 400 with 20 squared, and then we can FOIL this guy out, which would be 9 plus 6 times h squared plus h to the fourth. Just some simple algebra then to clean up that integral from that result right there. We can kick out that 1 over 400 coefficient to make our lives easier right there, and then we can run the integral for this entire expression of 9 plus 6h squared plus h to the fourth, running this down as 9h plus, this is going to be 2h to the third plus h to the fifth over 5, using exponent rule all the way down, and evaluate it from 0 to 10. Okay, so with that, we can then put this all the way through here. So this is pi over 400. Then evaluating at the 10 mark is going to be 90 plus 2 times 1,000 with 10 to the third power. And then 10 to the fifth is going to be 100,000 if we keep that all in mind there. But it will be over 5. Okay. And then zeros for the bottom limit going all the way down. Okay. There we go. Now we just have to run a couple of lines of simplification. We can take off a factor of 10 off these guys because each of them have a factor of 10 to give up. Then by doing this, this is going to be 200 for the middle term, and this will be 10,000 divided by 5, giving us lastly 2,000 as a result from that division. Okay, so this is going to be, if we add that all up, was it the 2209? So this is going to be pi over 40 multiplied by 2,209. Is that also a prime? Because there's no 40 has what? 40 has a 5. That's the only odd number in there, so I don't think there's anything else we can factor out from this. Yeah. Okay, so in this case, it's going to be 2,209 pi over 40. Because this is volume, there's going to be in inches cubed. We can leave it like this, and we should be just fine. Okay, very good. So with that, that's going to be part B there. A little bit of working around with integration, but nonetheless, the volume was found quite easily. Okay. Then part C, it's going to tell us that the funnel contains liquid that is draining from the bottom, okay, at the instant when the height of the liquid is h is equal to 3 inches, the radius of the liquid is decreasing at a rate of 1 over 5 inches per second. Okay, so they're asking that at this time, they're asking what is the rate of change of the height respect to time. Okay, so we've got a lot going for us right here because we're bringing the next element of time into this, because at a specific height we have the radius changing at a specific inches per second, but now we then need to know the height change and the height respect to time as well for this guy here. Okay, so what this means, of course, is that if we want to look at the change in the radius, so dr in respect to time, looks like we need to go and take that derivative, remembering that because we are looking for the change of height in respect to time, again, dh over dt is the target here, which in this case, a derivative of the height is not going to go to 1. This is going to be, of course, implicit differentiation that is being asked for right here. right? Because we're adding the time element to this. So by taking the derivative of radius respect to time, we take that radius equation of 1 over 20 times 3 plus h squared as was given at the start of the problem. But now we will derive this in respect to time. So we have ourselves just a little bit to work with here. I think first off, before we derive it, actually distributing the 1 over 20 will be a bit easier to keep track of everything that's going on here. That's 3 over 20 plus h squared over 20. And this guy will be taking its derivative, which because of this going across both of them, the 3 over 20 will go to 0, and then h squared over 20, keeping in track of chain rule, this will be h over 10 multiplied by dh over dt. Right? Chain rule, again, remembering that dh over dt will become our target that we're looking for, and the radius is changing respect to time as a result of that derivative. Okay, so with this, we have just about everything else filled out here, right? We have the height at 3 inches, the change in rate in inches per second, right? So we just need to isolate dh over dt. So with that, that's going to be dr over dt, then multiplied by the reciprocal of the h over 10 to move it over to the right side of the equation, which is 10 over h. Then we can plug in for everything that we do know. Dr over dt will be given that 1 over 5 inches per second as the units right there. And then 10 divided by the height given at 3 inches as well. Okay, so with this, 10 over 3 with a 1/5, that will give us, by canceling out the 5 and the 10, gives us 2/3 inches per second for the change in height in respect to time. Okay. Just a few lines of work here with keeping track of the implicit differentiation that is needed to solve for this part. Okay, so with that, we should be good right here for question number 5. So let's move on lastly to question number 6, and we shall be checking lastly on how well we scored overall on this packet. Okay, question number 6 has a nice and big table that I'm going to copy down over. So we have x over here, and moving down, we have f of x, then f prime of x, and then g of x, and then g prime of x. Okay, so with this, we have our points 1, 2, 3, and 6. Okay, so that is all the points that we're going to have on the x side. Fx goes -6, +2, +8, +4. Then f prime goes 3, -2, +7, +5. G becomes 2, -3, 6, and 3. Then g prime is 8, 0, 2, and -1. Okay, so something to note here is that as context, question number 6, they tells us that functions f and g have continuous second derivatives. Okay, right, and they give us that table as well. That's just a little bit of extra information, I'm sure, which might come to use later on in this problem. So first off, they're telling us that we want to let k of x be equal to f of g of x. Okay, then they want to say write an equation for the line tangent to the graph of k at x is equal to 3. Okay, so again, a tangent line, once more, they're doing that another time here, where it's going to be asking for the actual line at which, again, we need to look at the tangent line equation, given that's y is equal to m x minus h plus k for the function k of x, right? So because we're given x equal to 3, we actually need to know both the x and the y value for us to plug that into that equation. So let's get going with that first. So first off, again, this, if it's k of 3, we need to find the value. So that's saying with f of g of 3, plugging that directly into the equation right there. So starting first in the inner layer of this function, g of 3, so at x is equal to 3, the value of g on that table is going to be 6. So f of 6 is going to be that result. Then going to the next step, f of 6 is going to be positive 4. Okay, so at this we have the point 3, 4 as the coordinates. Then we're going to need to know that slope. Again, m in this case is going to be k prime of x, right? At the at the point x is equal to 3, which means we need to then find by doing k prime of x. That means we have to go and use our good old friend chain rule to take that derivative, given that we have a function in a function as a result of k. So with that, that's going to be f prime of g of x, then multiply by g prime of x. Simple chain rule that all students should be able to work on at this point. Then putting this through, this is at k prime of 3 to find that slope at x is equal to 3, meaning that it's f prime of g of 3 and then multiplied by g prime of 3. Okay, a few number things we need to fill out here to find that slope. G of 3, as before with our point already, is f prime of 6, right? But now we have to look at the f prime column there instead, and g prime of 3. So looking at x of 3, the g prime of x column is going to be positive 2, waiting there. F prime of 6, now f prime at the x is equal to 6, that column gives us positive 5. So 5 times 2 gives a result of positive 10. All right, so with that, we have both the point that we're looking at as well as the slope, right, at the point that we need. So with this, we can indeed find the line tangent here. Equation at y is equal to 10, that slope, x minus 3 plus 4 on the outside for k of x. Okay, very good. Took a few steps, but everything was pretty straightforward with finding the actual tangent line equation for something like this. Okay. Moving on to part B, they're telling us to let h of x now be equal to the fraction g of x over f of x. Now they want us to find h prime of 1. Okay, so with this, once more, we're hit square in the face again with something, of course, as quotient rule is needed for taking the derivative of this kind of fraction g over f. So with this, h prime of x is going to be, following quotient rule, is a low times the derivative of high. So that's numerator, g prime of x less high, g of x, derivative of low, f prime of x, all over squared below. So it's f of x, all of this guy squared. Quotient rule, something that will be needed to be memorized, but easily to follow up on as long as we have that in our minds. So now at h prime of 1, we just plug everything in here. So f of 1 times g prime of 1 subtracted by g of 1 times f prime of 1 all over f of 1, all that squared. Okay, so now we just follow everything on the table for these values. F of 1 then on the table right there being negative 6. G prime of 1 now being positive 8 subtracted by g of 1 being positive 2 and f prime of 1 then being positive 3. Then f of 1 back again is at negative 6 on the denominator, but all of that is squared. A very simple plugging in, and now we just solve for it. So we have negative 48 on the first term, minus a 6 all over positive 36 as a result on the denominator. So that is negative 54 over positive 36. The common factor here should be 9 across both of these, so that's going to give us, well, no, I think it's 18. Yeah, 18 and 3, yeah. So be taking out 18 is because negative 3 over positive 2 as a result of h prime of 1. Okay, pretty nice. So let's finish this guy off with question C here. They want us to now evaluate the definite integral from 1 to 3 of f double prime of 2x dx. Okay, so this is quite interesting. We need to go take a integral of a second derivative for this type of function, which of course we will need to appeal immediately to our fundamental theorem of calculus if we are looking to do any sort of work on definite integrals of derivatives, right? Fundamental theorem then would mean that we can take back one of those derivatives. So it's the first derivative. Now we plug in for 3, so it's f of x of the 2 times 3 and subtract it with the f prime of 2 times 1. Okay, so with that, that is just going to be the situation that we have there after taking the integral of a derivative, meaning that it's going to be the difference between. Actually, let me double check that, because if we're integrating, we're going to need actually a coefficient here in front as well. So before we do that, make sure we have the coefficient of 1/2 as a result of making sure that if we ran the integral, this is going to be f prime of 2x and then 1/2, because if we were to derive it back, that 2 will come out as a coefficient. Chain rule once more coming up to make sure that we are on track to make sure we don't make any of those mistakes. So with that, this is going to be 1/2 coefficient of f prime of 6 minus f prime of 2. Okay, so with that, we put everything through here. So 1/2 f prime of 6, back to our table again. F prime of 6 is positive 5, and f prime of 2 is going to be negative 2. Okay, so 5 minus a negative 2, giving us 1/2 times a 7, giving us 7 over 2 as a result. A little bit of a trap there set for us by the test makers, because that 1/2 coefficient is very important to keep us in line with the ideas of integration, with deriving f prime of 2x with that 1/2 coefficient there to make sure everything lines up the way they should. Okay, with that, that will conclude it for question number 6. So we should be good to then correct the remainder of our work here and see just how well we scored overall. Okay, so starting again at question number 5 here, let's swap back over to the answers here so that we can begin our corrections. Okay, so question number 5 was back to that cone question, or that's not cone, the funnel question, that is, where we have that radius in respect to the height from 0 to 10. Okay, so average value of the radius, of course, meant that we have to then start setting up for the average value equation, right, with the 1 over 10 coefficient, because that's the difference between the two limits on that integral. Then running through the actual radius function. By putting that through, we get the ending of 109 over 60 by running the actual integral, making sure we end up with 3h plus h cubed over 3 with the limits defined from 0 to 10. Right, this line of work was very important, as well as the setup, as well as the answer, all giving us 3 to 3 correct the way that they asked for in the answer key. All right, then moving down over to next part B, which is the volume of the funnel, right? They didn't show it in the simplest form first, but still the volume is shown here, but it is going to be pi multiplied by the integral of the radius squared times dh, right? Because the height is changing from 0 to 10, and the radius relies on that height function for it to actually give us the full volume. Okay, so this is the entire setup. And so we just then plug in for r, making sure we square the entirety of r, leaving that 1 over 20 coefficient to then change to a 1 over 400 after squaring it. So by running the actual integration of 9 plus 6h squared plus h to the 4th, and that gives us 9h plus 2h to the 3rd plus h to the 5th over 5, exactly the line of work that they want to see right there. Then running everything through, we'll get 2,209 pi over 40 inches cubed, exactly the answer that they were looking for. Did not need a calculator, even though it might seem a bit weird, just a lot of simplifying after running some algebra through. So both the setup, the actual step of integration, and then the limit analysis all will give us 3 out of 3 correct again right there. Okay. Lastly, let's move on down to part C here, which they were going to do. They wanted to find the change of height in respect to time. That meant they were looking for dh over dt. They gave us the change of radius in respect to time at the 1/5 inch per second. So again, that was what they gave us as dr over dt, right? And because of that, we then had to take the derivative of the radius in respect to height. By taking that, that's going to be as shown in this line of work, right? So we took the derivative. This gives us h over 10 as a result of canceling that out, right? And then dh over dt, because again, derivative h was what we were looking for at that implicit differentiation. Then by settling everything through, we end up indeed with negative 2 over 3 inches per second as a result. Okay, so everything does line up the way that they should, remembering chain rule of dh over dt being the result of that. Okay, so because of this, all that lines up correctly. That's going to be 3 out of 3 correct for part C as well. Okay, very good. So with that, that's problem number 5, giving us 9 out of 9 as we move on to question number 6 here. Question 5 is going to be 9 out of 9 correct as well. And lastly, moving to question number 6, where we have that table of those values of f, f prime, g, and g prime. Right? We run through first, looking at k of x being the f of g of x compound function right there. So with that, we were looking for the line tangent at x is equal to 3, that full equation, right? The setup was exactly what they wanted to see right there. Making sure we look at the actual point k of 3 giving us positive 4. That does match up exactly to find the actual y value first. Then by running the first derivative, keeping track of chain rule, right, the f prime of g of 3 times g prime of 3 for that line of work, we get a positive 10 after submitting everything through. And so the full answer of the 10 multiplied by all of x minus 3 plus 4 is exactly correct. Both the finding of the slope and the equation will give us 3 out of 3 correct for part A. Okay. Then moving on to part B here, it's going to be the h prime, this time with the fraction of g over f of that. So once more, we have to do quotient rule for h prime of 1. So f of 1 multiplied by g prime of 1, subtracted by g of 1 multiplied by f prime of 1, all divided by f of 1, all that squared. Everything works through. Negative 3 over 2 is exactly what we need. Again, keeping track of quotient rule all the way through with the right answer giving us 3 to 3 correct over there. And lastly, an evaluation of that second derivative integral. Of course, I did catch that before we submitted our answer, is that that 1/2 coefficient must be accounted for because f prime of 2x will give us a 2 coefficient after taking its derivative as a check of the answer. Then evaluating it then from 1 to 3, right, giving us f prime of 6 minus f prime of 2 inside with a 1/2 coefficient on the outside, leaving us lastly with 7 over 2 as a result of that evaluation. Okay, everything matched up exactly the way they needed to, giving us another 3 out of 3 correct over there. Okay, and that marks another time in our books where we get 9 out of 9 all the way down the entire test packet, giving us 54 out of 54. A lovely perfect score once more in the books as we are nearing the last week of preparation. Again, just as a little bit of an update for what we are currently working on is that we are going to do our last video of calculus currently in the works. We'll be putting these last final touches through. Again, should be the entirety of what we've been working on so far, and then we'll be moving on to other topics like chemistry for this channel, as well as other projects that we'll be undertaking. So once again, thank you for coming in through here with looking and witnessing another perfect score for our AP Calculus practice. Again, this entire recording will be on the channel itself. Again, for anyone else to view and follow along with, all these questions are on College Board directly, in which you can follow along step by step for those who are studying the AP Calculus exam. So once again, thank you all for tuning in today. We definitely would like to see you another time as we move forward on these next parts. And hopefully from there, we should be just about good to go with the exam coming up on May 12th. So thank you everyone for tuning in, and we hopefully will see you again next time.